think about your bank account for a second. I want you to imagine it as a highly secure, heavily fortified vault with your hard-earned balance safely locked away inside. It's tucked away, totally shielded from the chaos of the outside world, and absolutely safe from anyone trying to just dip their hands in. So think about how that vault actually operates. If you open up your banking app right now, can you just tap your balance and manually type in $1 million? I mean, I wish, but obviously no. Nobody can reach in and just randomly alter their balance. Changes only happen through very specific, tightly controlled actions, like explicitly depositing funds or withdrawing them. You always have to go through the proper channels. Well, that everyday restriction is literally the exact idea behind today's concept, encapsulation. That restriction at the bank is the very foundation of how we build reliable software. Without it, we'd be left with chaotic, unencapsulated code, where data could just be manipulated randomly from the outside by any other piece of the program. Imagine if any random part of a shopping app could just subtract from your bank balance without even checking if you had enough funds. Encapsulation acts as the bank vault of software to prevent that exact kind of disaster. If we're getting technical for a moment, encapsulation is basically the process of bundling your data, the variables, and the methods that operate on that data into one single cohesive unit, which we usually call a class. But the second half of that definition is just as critical. It restricts direct access to that data from the outside. You can picture it visually as a protective capsule. Inside, your private data is glowing safely, totally inaccessible directly from the outside environment. The only way you're interacting with that data is through the capsule's explicitly built-in interfaces. Now, this protective capsule actually works using a strict set of rules, which we define using access modifiers. Think of these as color-coded security rings surrounding our capsule, dictating exactly who can reach which layer. Number 1 is private. This means the data is completely locked inside. Honestly, only the class itself even knows it exists. Number 2 is protected. That one is slightly looser. It grants access to the class and its immediate subclasses, kind of like giving a VIP pass to trusted family members. And finally, number 3 is public, meaning that method or data is accessible from absolutely anywhere in the software. It's really fascinating to see the security system in action. Let's say we have our bank account class, and the balance is marked private. If some external code tries to reach right in and overwrite that private balance variable, the system throws an error. It flat out fails, as it should. However, if that external code uses the public deposit or withdraw doors located on the capsule's surface, the action succeeds perfectly. The capsule is in total control of its own internal state, 100% of the time. So, you're probably wondering, if the data is totally locked away as private, how on earth do we actually use it? Well, we build very specific public doors, which brings us to a super common pattern: getters and setters. A getter door lets outside code read a private value safely. It's like asking a bank teller for your account balance. You can look at the number on the screen, sure, but you can't reach through the glass and change it. A setter door, on the other hand, lets outside code update a value, but only after passing through a gatekeeper that ensures the new value actually makes sense. And here is the absolute crucial point. Encapsulation isn't just about hiding data to be secretive. It actively protects the object from ending up in an invalid state. We call this setter validation. When you try to set a new value, the setter method can run checks, do some math, or even verify credentials before it ever actually updates that private data locked inside. Think of the setter method as a ruthless bouncer at a club, aggressively rejecting invalid inputs. If a program tries to withdraw $100 from an account that only has $50, the setter rejects it. If a user profile form tries to set someone's age to a negative number, reject it. Or say in a GPS app, if the system tries to set a latitude coordinate way beyond 90 degrees, the setter can either reject it or use math to correct it before saving it. The data stays completely pristine. Now, banking is the classic example, right? But the truth is, this concept goes way beyond banking. Virtually every professional, well-designed codebase on the planet operates this way by default. Encapsulation is everywhere. It's literally the invisible scaffolding holding up the apps on your phone and the software running your entire computer. just think about driving a car. Your dashboard gives you read access to your speed and your gas levels, but it never ever exposes the raw, complex engine wiring or the fuel injection systems directly to you. Instead, you're given a gas pedal, which is basically a public setter method that safely tells the engine to accelerate. You aren't manually injecting fuel into the cylinders yourself, because if you did, you'd almost certainly break the engine and totally void your warranty in the process. It is the exact same logic when you look at cybersecurity systems. A well-built login system never exposes a raw password field or a session token directly to the rest of the application. It acts exclusively through strictly validated authentication methods. And this guarantees that no other random part of the software can accidentally leak or overwrite the current user session. The whole security model relies heavily on these strict boundaries. All right, so understanding all this actually helps us bust a massive myth that trips up so many people. Does encapsulation just mean slopping the word private in front of all your variables? A lot of people think it's just about locking things away in a dark room, but it's not. It is specifically about controlled access through methods. It's the active bundling of the data and the rules that govern that data together. And that brings up another thing people mix up all the time: encapsulation versus abstraction. But the distinction is actually pretty clear. Encapsulation focuses on how data is accessed, with the main purpose being data hiding and restriction. Abstraction is an entirely different beast. It focuses on what the object does, with the purpose of hiding complex implementation details so you only see the essential behavior. Basically, encapsulation hides the data, abstraction hides the complexity. We also need to clarify something else. Encapsulation is not exactly the same thing as the design principle of information hiding. Fun fact, when information hiding was first introduced by David Parnas in the early 1970s, some critics, like the famous computer scientist Fred Brooks, actually called it a recipe for disaster, though Brooks later admitted he was completely wrong about that. Today, we know it's a core design principle for building secure systems. Encapsulation is just the specific language feature that facilitates information hiding. It doesn't strictly guarantee it, because honestly, you can encapsulate poorly and still expose way too much info. And this leads me to a really, really important piece of advice. Please do not assume that every single variable in your class needs a getter and a setter. Just don't do it. Not everything needs a public door. Some fields are purely internal mechanics that should stay fully locked away. If nothing outside the class legitimately needs to touch a piece of data, give it no getter and no setter. Keep that capsule sealed tight. So, zooming out for a second to the macro level, why does all of this actually matter? Why do senior engineers obsess over this stuff? Because encapsulation is the absolute secret sauce to making massive, complex code bases incredibly maintainable. By strictly controlling access, you prevent misuse. And it makes unit testing so much easier, because you can test a single class in complete isolation, knowing its state can't be secretly altered by some random bug elsewhere in the program. But honestly, the biggest advantage here is that internal changes don't break external dependencies. Thanks to encapsulation, you can completely gut the internal implementation of a class. Say you decide you want to store that bank balance in a database instead of just a simple variable. As long as those public deposit and withdraw methods take the exact same inputs and give the exact same outputs, none of the external code relying on that class is going to break. The rest of the software doesn't even know the internal plumbing changed. Now, this explainer has been part one of our deep dive into the pillars of object-oriented programming. We've officially mastered the protective capsule, so I invite you to follow along for our next explainer, where we're going to tackle abstraction and learn how to simplify massive complexity by exposing only what truly matters to the user. But before you write your very next line of code, I want you to ask yourself, what critical piece of data in your current project is sitting completely exposed right now, just waiting for another part of the system to accidentally break it? Thank you for watching the Tech Canvas. Complex ideas, clear pictures. Follow for more.